In this example, we can practice our properties of logarithms to combine these expressions together to form a single logarithm. So here we have the natural log of a plus 1/2 times the natural log of b. One property we can remember is that when I have the factor multiplied in front of the logarithm, we can bring it in the logarithm as a power. So we'll do that first. Write this as ln of b to the 1/2 power. And now that I have a sum of these two logarithms, they can be combined together by multiplying a times b to the 1/2. So now we've combined them together into a single logarithm. In fact, we can go one step further and just write the square root of b. Here's one more important property, which is changing a base. So for any positive b, we have this property that log base b of x can be written as ln of x over ln of b. Now this could actually be any base, but we'll see in particular it's going to be very useful to do this with the natural log. So here's a quick little proof. I'll start by writing log base b of x and then equal it to y. And now this allows me to express this in its exponential form. So I can write this as b to the power of y equals x. And now what I can do is apply the natural log to both sides of this equation. Once I do that, I can apply the property of logarithms that allows me to take that power of y outside the log. So this becomes y times ln of b equals ln of x. And now by isolating y, I have my result. Y equals ln of x over ln of b, which gives me the equation. Log base b of x equals ln of x over ln of b. And why is this useful? One particular reason this is useful is because it allows us now to always express a logarithm of any base in terms of the natural log. And we'll see that when it comes to taking derivatives, that the natural log is going to be very nice for doing derivatives because it has a very simple formula. Another reason why it might be useful would be just for evaluating purposes. Say for instance I want to evaluate log base 8 of 5. Well, on my calculator I don't have a button that allows me to do log base 8 directly, but I can convert it to natural log and use the natural log button on my calculator. So log base 8 of 5 I can write as ln of 5 over ln of 8. And now I can simply type that into my calculator. My calculator, of course, has ln of 5, and then I'll divide by ln of 8. That gives me something around 0.7739. I'll say 0.774. And you may also notice that your calculator does have the common log, log base 10. So you could do the same thing with common log as well. This would be log of 5 over log of 8 would give you the same result. But here we'll see why we're using the natural log in the next section when we look at its derivative. Let's consider the behavior of the natural log as x goes to infinity and as x approaches 0 from the right. It's exactly the same as what it was for log base b, where the base is greater than 1. We see that the graph of ln of x is the graph of e to the x shifted or reflected across the line y equals x. And so, yeah, we see it inherits those same properties that the log base b of x graph does. So let's think about what our graph of ln of x minus 2 minus 1 looks like. Notice there's two basic transformations here. X minus 2 inside the parentheses is going to shift left. It's going to shift right 2 units. And then the minus 1 here is going to shift down 1 unit. So thinking of the natural logarithm originally has that point at 0, 1. At 1, 0. So we're going to shift it 2 units to the right and then 1 unit down. So that point now shifts over here. In addition, the original ln of x graph we know has a vertical asymptote on the y-axis. Since we're shifting the graph 2 units to the right, that vertical asymptote is also going to get shifted 2 units to the right. And then from there we can apply the properties that we know. For instance, it will approach negative infinity here as it approaches the vertical asymptote, and then it'll continue to rise as it goes to the right.